All right, so I'm going to go over the solutions to the mock exam I gave you last week, and I want to do these in sets of 10, so there will actually be 5 of these videos. Let's take a look at number 1. We are told that hydrogen and chlorine react explosively at high temperature to form hydrogen chloride gas. When these two reagents are mixed at room temperature, they do not react in a reasonable amount of time. Okay, so there's a couple of conclusions we can draw from this, but I think there are some larger principles that this question illustrates, and let's take a look at those principles. Remember, from the philosophy of chemical reactions, thermodynamics answers the question, will I be able to produce a reasonable amount of product? Kinetics answers the question, how fast will I be able to produce a reasonable amount of product? And equilibrium asks, how much product will I produce? Of course, we can relate thermo and equilibrium quite nicely with the relation that delta G is equal to minus RT times the natural log of the equilibrium constant. So I can relate thermo to equilibrium pretty easily. Relating thermo to kinetics is much more difficult, although there is a weak connection in the fact that the energy of activation is the delta G of the transition state. So kinetics, if we look at a potential energy diagram, is typically going to implicate the activation energy. While thermo, in terms of a potential energy diagram, implicates whether the reaction has a positive or negative delta H. Of course, this will be exothermic if it has a negative delta H, and it will be endothermic if it has a positive delta H. Now, we've seen this before, but let's go over it one more time. Let's look at the potential energy diagram. And if we look at, let's look at enthalpy, or H, as a function of reaction coordinate. Reaction coordinate just maps the course of the reaction from time equals 0 to time equals t, where t is where the reaction is quenched or stopped. So we have the energy of our reactants. We have the energy of our products. We'll simplify and assume this is a one-step reaction. This is our transition state. Of course, energy of reactants, energy of products. The difference between the energy of reactants and energy of products is the delta H. This is an example of an exothermic reaction because delta H is equal to the H of products minus the H of reactants. And when you take a smaller positive number and subtract from it a larger positive number, you'll always get a negative value. For example, if we had 5 minus 10, the answer to that would be minus 5. The distance from the transition state to the energy of the reactants is called the energy of activation for the forward reaction. On the other hand, if I go from the transition state to the energy of the products, that's the energy of activation for the reverse reaction. Notice in an exothermic reaction, the energy of activation for the forward reaction is smaller than the energy of activation for the reverse reaction. So we're told in problem 1 that this reaction will not proceed at low temperatures. First of all, that means we have a high energy of activation barrier. Secondly, we're told that at high temperatures it reacts explosively. That means we have an exothermic reaction. So if we put these two pieces of data together, we know that it's exothermic, so let's eliminate A and let's eliminate C. And we know it has a high activation energy, let's eliminate D. B is the credited response. B is the answer that we want to pick. Let's move on to question number 2. Hydrogen iodide is decomposed according to the following balanced equation. They give you a balanced equation. They do not give you any idea if this occurs in one step or in multiple steps. And quite honestly, you cannot make a rational conclusion regarding the kinetics of this reaction. So the best answer is going to be D. You would need to have data or a proposed mechanism that has some validity to it. Let's move on to number 3. We want to calculate the pH of a 0.25 molar solution of chloroacetic acid. This is a kind of problem we emphasize over and over and over again in this course. So let's take a look at it. So we have a weak acid HA that is 0.25 molar. And we're going to use the dissociation equation that we've used so many times in class. We know that the Ka is 10 to the minus pKa, which is 2.86. And this leads to hydronium and the conjugate base, which is chloroacetate. Initially, this is what they have. Some of this will decompose to produce product. We're going to use our assumption that 0.25 minus X is essentially 0.25 because our initial concentration is greater than our Ka by a pretty significant factor. So we know that X squared over 0.25 is equal to the Ka, which is 10 to the minus 2.86. Everything else now is just going to be mathematics. So X is going to equal the square root of 0.25 times 10 to the minus 2.86. And if we simplify this on calculator, we get 0.0186 molar. That's our concentration of hydronium. To go from hydronium to pH, of course, we're just going to take the negative log of 0.0186 molar. And when we do this, get an answer of 1.73. And that is credited response B. So the answer for number 3 is B. All right, moving on to number 4. We are given the solubility of barium fluoride at a certain temperature, and we want to calculate the KSP at the given temperature. So again, it's all going to start with a balanced chemical equation. BaF2, you really need to know ions and charges. And of course, this is not aqueous, this is a solid, and I'm going to use a darker color. So we got barium fluoride that is solid, and its molar solubility is 0.0018 molar. .018 molar, excuse me. Of course, KSP is what we're trying to find. This is going to dissociate into a barium 2+ ion. And this is important, 2 fluoride ions. So if this is 0.0018 molar, barium must be 0.018 molar, but fluoride must be 0.036 molar because of the 2 to 1 stoichiometry. So now KSP is going to be equal to the concentration of Ba2+ times the concentration of F- to the second power. Plugging this in, we have 0.018 times 0.036 squared. Now, of course, we're going to simplify this with our calculator. And I obtain an answer of 2.33 times 10 to the minus 5. And that's going to be answer C. So for number 4, the credited response is going to be C. All right, so when we look at number 5, we have a competition between two acids, fluoroacetic and chloroacetic. They're identical except for chloroacetic replaces one of the hydrogens with a chlorine, whereas fluoroacetic replaces one of the hydrogens with a fluorine. And the overriding effect here is called the inductive effect. Which of these two atoms can best help stabilize the negative charge in the conjugate base? And so the overriding principle here is going to be electronegativity. And fluorine is more electronegative than chlorine. So fluoroacetic would be the stronger acid because of the electronegativity of fluorine over chlorine. So as we look at our answer choices, A is wrong, B is wrong, C has the right acid but for the wrong reason. D is the best answer. So D is the credited response. Moving on to number 6. You have a chemical reaction that has a negative delta H, which means it's exothermic. It has a positive delta S. This means the delta G will be negative, and the K value must be greater than 1, always. Best answer is answer choice A. All right, moving on to number 7. We want to look at our electrochemical cell, and we see that we have a KNO3 salt bridge. We see the electrons are moving away from the electrode to the right towards the electrode to the left. What's important about that is that we learned this year that the electrons move from the anode towards the cathode. Of course, anode is where oxidation takes place, and the cathode is where reduction takes place. So oxidation is the loss of electrons, and of course the electrons are moving from the anode to the cathode. So oxidation is going to take place in the right cell, reduction takes place in the left cell. So we need to identify the cathode. That's going to be B. Number 8, the purpose of, that should be salt bridge. The purpose of the salt bridge is so that we don't build up charge and prematurely quench the reaction. That's going to be D. Number 9, where will the nitrate ion be at equilibrium? The nitrate, the anion, goes to the anode, so it's going to go to C. So number 9 is C. And where would the anode be if the cell is electrolytic? Well, if the cell is electrolytic, the electrons move towards the anode. So the anode would be B if the cell was electrolytic. The only difference between an electrolytic cell and a galvanic cell is spontaneity. So in a galvanic cell, you have a spontaneous cell that produces a current. So you're converting chemical energy to electrical energy. In an electrolytic cell, you're converting electrical energy to chemical energy. Also, electrons flow from anode to cathode in galvanic or voltaic. They flow from cathode to anode in the electrolytic because there's a battery, a current source that must be used to flow the electrons. All right, so this takes us through the first 10 solutions. I'm going to stop this and then we'll pick up with question 11 on the following screencasts.